today's topic of discussion is optical fiber. Before I go into the detail of components of its, I want to state some historical background of the optical fiber. Prior to about 1980s, most communication technology involved some type of electrical transmission mechanism. The era of electrical communication started in 1837 within the invention of the telegraph by F.B. Morse. Later in 1876, Graham Bell developed a fundamentally different device that could transmit the entire voicemail as an in analog form. So as research and development progressed, the first installed optical fiber links, which appeared in the late 1970s after the discovery of the laser, were used for transmitting telephony signals at about 6 megabytes per second over distances of around 10 kilometers. If we compare the advantages of the optical fiber with the copper wire, through which we have seen that signal transmit through the electrical energy form, so the optical fiber advantages are it carry long distance transmission. Number 2 advantage of the optical fiber is for the large information capacity. Number 3, as compared to the copper wire, its advantage is that for a small size and low weight. And fourth advantage of the optical fiber is enhanced safety. So security into the signal is more important in optical fibers as compared to the copper wire. So these are some basic points, historical background of the optical fiber. As many people know about the main principle behind of this optical fiber is total internal reflection. So the first step of this optical fiber lecture will be explanation related to the law of reflection. So as we know that we define refractive index in terms of the speed of light in any medium and speed of light in a vacuum. So N, that is the refractive index, is defined by the ratio of the speed of light in vacuum and speed of light in any medium. So there are some refractive index of water. N is equal to 1, that is for air. N is equal to 1.33, this is for water. N is equal to 1.45, this is the silica glass. N is equal to 2.42, this is for diamond. So these are some example of the refractive indices. So you have seen here that the refractive index of the air is 1. So speed of the light in air and speed of the light in vacuum, that is same. So C is equal to V. But in case of water, we are observing that N is equal to 1.33, N is equal to 1.45. This basically is the ratio of speed of light in vacuum and speed of light in any medium. So now the next point is about the ray theory, by which I have to explain the total internal reflection. So the title is the ray theory transmission. So for this purpose, I have selected two medium. This is N1. For the first medium, the refractive index is N1. Second medium is which refractive index is N2, and the condition is that the refractive index of the first medium is greater than the refractive index of the second medium. So this line basically is dividing the two medium 1 which have refractive index N1 and second medium that have refractive index N2. And now this is the normal. So a light ray basically incident into this medium and makes an angle Fibre with the normal. It basically partially refract into the second medium and partially reflect into the same medium again. So this angle from the normal is phi 2, and this you can say is theta 2, and this is theta 1. So this ray is refracted ray, and this ray is reflected ray. This one is the material boundary. This is material boundary, and this was the incident ray. So this happened when a incident light ray falls on this particular point. This medium is rare as compared to this one, so light ray basically go away from the normal, right? And this is the partially reflecting into the same medium. This is partially refraction. So now by using this geometrical optics, we have to explain this transmission of light into the optical fiber. Before I go into the detail of that TIR, total internal reflection, the TIR stands for total internal reflection. So here you can see the refraction and reflection. This one is the incident ray. So the relationship at the interface at this point you can find out by using the Snell's law. So now I am using Snell's law at this interface. So this is first medium, refractive index is of that N1. So N1, this angle sin phi 1 will be equal to this one, and that is second medium, which have refractive index n2. So according to the Snell's law, at this particular point, this will satisfy the condition n1 sin phi 1 is equal to n2 sin phi 2. So here n1 is the refractive index of the core and n2 is the refractive index of this medium. Phi 1 is the incident angle and phi 2 is the refracted angle. And in terms of theta 1, you can say that n1 cos theta 1 is equal to n2 cos theta 2. But the point is that this theta 1 is the angle for incident ray with this material boundary, and phi 1 is the angle of this incident ray with respect to the normal, and similarly for theta 2 is the angle for reflected ray with the material boundary, and phi 2 is the angle of refracted ray with the normal. So this is the relationship between the theta 1 and theta 2, phi 1 and phi 2. Now we have to see total internal reflection, how it basically take place. So again, for the total internal reflection, we have to use two mediums. This is medium 1. Refractive index is of that n1. This is second medium. Refractive index of this is n2. So, and now this is the normal at this boundary of the two medium. So when a light ray incident on it, then there are basically, I have explained this total internal reflection in three pictures. The total internal reflection. This one is the incident ray. Makes an angle phi 1 with the normal and refracted into the second medium and makes an angle phi 2 with the normal. So this is exit ray that basically is refracted ray, and it partially reflect into the same medium. So this is partial internal reflection. So you know that this medium N2 is rare as compared to the first medium. It means N1 is greater than N2 always. So this is first medium, this is second medium. Ray enter through the first medium and refracted through the second medium. And now if suppose I increase this angle little bit from the phi 1, so right now the angle is this one. I have increased this phi 1. I am increasing the angle right now, so the light will bend more into the second medium. So this will be phi 2 right now. So phi 1 is the incident angle, right, for this black line you have seen, and now I am using this green color for the second ray. Its angle is greater as compared to the phi 1, and it will bend more as compared to this black line. So if the third situation, if I again increase the angle, and now this is the phi 1, the third case, it basically passes through the medium. The ray basically will pass through the medium, that is the interface of these two mediums, first and second. So now this will be of 90 degree. Now phi 2, the angle of refraction for the third case is 90 degree, and in this situation basically this phi 1 is known as critical angle. When the ray, refracted ray, makes an angle of 90 degree, then we say that this phi 1 will be critical angle. So phi 1 is critical angle. This will be critical angle only when the refracted ray makes an 90 degree angle. So phi 1 is equal to phi c, that is the critical angle when phi 2 is 90 degree. It means the ray basically passes through the interface of these two mediums. And if suppose I increase the angle of incident ray little bit, it gets totally reflected into the same medium, right? So it will reflect into the same medium. So this is the fourth case where I am increasing the angle of incident ray, that is greater than the critical angle. So in this situation, the light ray basically get reflected into the same medium, and this particular phenomena is known as total internal reflection. So for the total internal reflection, phi 1 should be greater than phi c. Phi 1 is the incidence angle, right? And it should be greater than critical angle. And how I define the critical angle? Critical angle is the incidence angle, and it is only when phi 2 is of 90 degree. It means the refracted ray makes of 90 degree angle. So this particular situation is explained through this total internal reflection, or you can say this is the total internal reflection of a incident ray into the same medium. So here what I explain, I use first ray that makes an angle phi 1 refracted into the same medium, reflected into the same medium partially, and refracted here, that is the second medium, makes an angle phi 2. Then I use this green color light ray, that is the second case, and again I am increasing the angle, and because of that it bending away from the normal. And similarly for the third case, so in the third case I have shown here that it passes through the interface of the two medium, and if I little bit increase, that is the fourth case, this black line, it will totally get reflected into the same medium, and this is known as total internal reflection. So once again, phi critical angle is the incidence angle, and it is called when the refracted ray makes 90 degree angle, and total internal reflection will take place only when this incidence angle is greater than the critical angle. So now this is the important point for the optical fiber. So if suppose in the fourth case you have seen that the light ray get reflected into the same medium, and in the third case you have seen that this light ray basically refracted through the interface of these two medium. It passes through here. So if I apply the Snell's law here, then let us see what happens. So n1 sin phi 1 is equal to n2 sin phi 2, right? This is the Snell's law at the interface where light ray incident. So n1 is the refractive index, will remain as it is. Phi 1 is the critical angle. So sin phi c is equal to n2. When phi 1 is equal to phi c, phi 2 will be or phi by 2, 90 degree. So n2 sin 90 degree. And sin 90 is equal to 1. So n1 sin phi c is equal to n2 into 1, or sin phi c you can say is n2 upon n1. So if one have to find out the critical angle, then what will be the requirement? The requirement will be only the two refractive indices, n1 and n2. If these two are available, only then one can find out the solution for the critical angle. So phi c is equal to sin inverse of n2 upon n1. So this is the first formula to calculate the critical angle, and this relationship you develop only for the condition of critical angle by using the Snell's law of reflection, right? So this is the total internal reflection, the first part. Now the second part we have to discuss about the acceptance angle and the numerical aperture. So in this section, the next one after the total internal reflection, I have to discuss about the transmission of light ray in a perfect optical fiber. So the next point is about the transmission of the light into an optical fiber. So optical fiber mainly have two components. One is the core and second is the cladding. The refractive index of the core is defined by the N1 and refractive index of the cladding is defined by the N2. And relationship between these two refractive indices is always that N1 is greater than N2. The refractive index of the core is always greater than the refractive index of the cladding. And the third one is buffer coating. It basically protects the core and cladding. If I draw it, so the central part of the optical fiber is core. This is central axis and the core. This is core, refractive index is M1, and second is cladding. So this one is cladding. The refractive index of this is N2, and to protect this core and cladding, the next is buffer coating. This one is enclosed by the buffer coating. So this is the basic structure of the optical fiber. This is the core, this one is the cladding, and refractive index of the core is N1, refractive index of the cladding is N2, and all these two things basically is covered by this coating, buffer coating, which is known as buffer coating. So now the first point in optical fiber is about the acceptance angle. What is the acceptance angle? It basically denoted by the theta A. This is the maximum angle at which basically light ray enter and get reflected, totally reflected inside the core. So this I am using the same diagram. So this is the central axis of the core or this optical fiber. If this is the interface, this optical fiber is kept into the air. So the refractive index of the air is N0. As I told earlier, the refractive index of the core is N1, and for the cladding it is N2. So what is the acceptance angle? How one can define acceptance angle for the optical fiber? So for that I am using this point, that is at the air and core interface, and a light ray, basically this one, enter into the core. Refractive index of the core is greater than the refractive index of the air. So it will enter into the core, and at this particular point, that is the core cladding interface, here it get reflected, and again reflection from the core cladding interface. This is possible only when this incident ray for the core, inside the core, is make that angle basically which it makes with the normal is greater than the critical angle. So to show that, I am drawing a normal here, taking a normal at this particular point. So this normal I have drawn here, that this angle is phi 1 and it will be again same, that is phi 1. If suppose this incident angle is theta 1, so this will be refracted angle and it is denoted by theta 2. So theta 1 is the incident angle and theta 2 is the refracted angle. Phi 1 is the angle at the core cladding interface. So the point is about acceptance angle. If suppose, before I explain about the acceptance angle, I am taking one more light ray that basically enter at this particular angle. So angle of this light ray is this one. So one can say this is suppose theta prime. So this light ray basically enters into the core, but it does not reflect inside the core medium. It passes through the cladding like this one. So this light ray, which makes a greater angle as compared to the first case, enter into the cladding. What is the reason of it? And why in the case of one, this light ray get multiple reflection inside the core by satisfying the condition of TIR. So point is that the light ray which basically reflecting from the core cladding interface is satisfying the condition of critical angle. So here this light ray basically which makes an angle phi 1, that angle is greater than the critical angle, right? So if for the second case this light ray does not enter into the core, does not get multiple reflection because it enters into the cladding because of this reason. Its angle is higher as compared to the first case. So this particular angle theta 1 is the maximum angle with respect to the axis at which all the rays basically which enter between these two get multiple reflections into the core. So if I draw it proper in a cone shape, so I am taking another extreme rays towards this side. So this is theta 1 I can say, and again this light ray enter into the core and get reflect 100%, and again the reflect. So this maximum angle at which light get multiple reflections inside the core is known as acceptance angle. So I am making this in a proper shape, this cone, to making this concept more simple. So now all the rays basically which enters through this cone, they will get multiple reflections into the core. And if any ray enter into the core beyond this limit, that basically will pass through this cladding and not useful for the communication purpose. So this angle theta 1, the maximum angle, is known as acceptance angle. So the acceptance angle is theta A, at which all the light ray get reflections inside the core. So this is the basic idea of the acceptance angle. And now the next point is about the numerical aperture. So to explain the numerical aperture, we have to again use the same diagram in same way. Numerical aperture basically provide the relationship about acceptance angle and the refractive indices of the core and cladding, and the fractional refractive indices. But mainly we define numerical aperture a relationship between the refractive indices and the acceptance angle. So the next topic is about the numerical aperture. So numerical aperture basically a relationship between the acceptance angle and the refractive indices of the three media involved, namely the core, cladding and air. So again we have assumed here that this optical fiber is kept into the air, so we are using the refractive index of the air also. So now the geometry for the numerical aperture is this one, where this one represent to the central axis of the core, this red color light ray, this one is the extreme ray. This is known as extreme ray, which makes a theta A angle, that is the acceptance angle. The maximum angle at which the light ray enter into the optical fiber and where multiple reflection take place, that ray is known as meridional ray, or sometimes it is called extreme ray. So on both sides you can make it, and this is acceptance cone, and this angle with respect to the central axis to the extreme ray is the maximum angle theta A, that is known as acceptance angle. So here, as I told earlier, that this is the theta 1 angle, is known as incident angle at the air core interface. This light get refracted inside the core and get multiple reflection because of the TIR. Here it makes theta 2 angle, that is the refracted angle into the core, makes by this ray 1. This is the core cladding interface. Here this ray, incident ray, inside the core makes an angle phi 1 and get reflected totally and enter and travel like this, in this way. I have drawn a normal here. So this is a triangle. This angle is theta 2, this angle is phi 1, and this is 90 degree, pi by 2. So in case of numerical aperture, to define the numerical aperture, in the definition we said that this is the relationship between n0, n1 and n2, right, and also with the theta A, that is the acceptance angle, that is the maximum angle. So for this purpose, to define the numerical aperture, we have to apply again Snell's law at this particular point. That is the air core interface. So at air core interface I have to apply Snell's law, and that is, so by using Snell's law at the air and core. This is air, this one is core. Refractive index of the core is N1. This is cladding. Refractive index is N2. Refractive index of the air is N0. So we are applying the Snell's law at the air core interface. So N0 sin theta 1 is equal to N1 sin theta 2. This is our first equation. So I have applied the Snell's law at this interface, and we observe this equation where N0 is the refractive index of the air, theta 1 is the incident angle, N1 refractive index of the core, theta 2 is this refracted angle. So now, considering the triangle, this is A point, this is B point, and this one is the C. So triangle ABC, where this B is of 90 degree. So considering the triangle ABC, here sum of these two angles phi 1 and theta 2 is of 90 degree. So phi 1 plus theta 2 is of 90 degree. So phi 1 is this angle and theta 2 is this one. The sum of these two angles is of 90 degree. So I have to use basically this relation to put the value of theta 2 in equation number 1. So theta 2 is equal to pi by 2 minus phi 1. So now I have to use this value in equation number 1 here. So it becomes N0 sin theta 1 is equal to N1 sin theta 2, and when sin theta 2 is equal to 90 minus phi 1, that is 90 minus phi 1, it becomes cos phi 1. So instead of writing this sin 90 minus phi 1, I have to write cos phi 1. So this is N1 cos phi. This is second equation. So for this equation I have used this triangle ABC, where theta 2 was the refracted angle and phi 1 was the critical angle. So N0 sin theta 1 is equal to N1 cos phi 1. Now the third step is to change this phi 1, cos phi 1, because we know the relationship sin square phi 1 or sin square phi plus cos square phi is equal to 1, right? So here this is cos phi 1, so that can be written as is equal to 1 minus sin square phi or cos phi further is equal to square root 1 minus sine square phi. So now in the limiting case, the limiting case is what? That this phi 1 should be greater than the critical angle. Right? So this phi should be greater than the critical angle. Only then it will get reflect totally into the core. So by using this property, one can write that in the limiting case, one can write here properly. In the limiting case, theta 1 becomes the acceptance angle for the case theta e, for the case theta e, right?